Hello, Luke here. In the last episode of this series, we were gathering together our training data for the machine learning model, and we grabbed the positives. We grabbed the actual, in our case, it's hermit thrush song. In your case, it might be something different, but we grabbed positive hermit thrush songs. And now we need to think about grabbing an equivalent amount of negatives. So just going back to the actual spectrograms in Raven, and of course you can use whatever software you want, but we're looking here and we're going to be grabbing, these 1.5 second images that are positives, and now we want negatives, so stuff just in between, like this, and maybe stuff that has half of a song, and maybe other stuff that has this, the first half is not aligned properly. And so we got to decide, when is it a negative image? When is it not a hermit thrush song? And we've got to make some choices here. And the number I'm going to put on this is zero point 0.2 seconds. So you can see if I zoom in, these boxes are not totally precise. People have boxed around these images, and they've done it quickly, and they've done it zoomed out, and so there's going to be gaps. There's going to be error, and we have to work with the data we've got. So in this case, it's like 0.05 seconds of silence before the song, and that's kind of error. But sometimes it's worse than that. Sometimes it might be like back here where they've boxed, and sometimes it might be late and they boxed like this. And so there's a certain amount of error in our positive hits that our machine learning model needs to deal with, and we need to send it a clear message of what is correct and what is incorrect. So our correct has this wiggle room of zero point 0.2 seconds. So our incorrect needs to kind of accommodate that wiggle room, so we can have a clear distinction. And so that's what I'm going to do, is I'm going to grab random images from the spectrogram that are at least 0.2 seconds away from the left edge of these selections, so that I don't accidentally feed my machine learning model positive actual hermit thrush song and tell it that it's not right. I want to tell the right message to my machine learning model. Hopefully that makes sense. So what we're going to do is start grabbing random images, and we're going to work with that and see what we get. So first I'm going to import random. That's the library that deals with grabbing random numbers. This is the loop we had last time for grabbing positive images. And so what I'm going to start doing now is I'm going to make a while loop that's going to grab random numbers for the start times of these images. I'm just going to make it go to 5 right now, because I don't want it to run 447 times. But eventually that's what we want, is for it to run that. And as soon as you make this, I would always add the incrementer right away, because otherwise you end up with an infinite loop. Whenever hopefully your spider senses go off when you type while, because it's very easy to accidentally write an infinite loop. Right now it won't be, but as we work, we might. What we want to keep thinking about: did we accidentally make something that doesn't actually finish, doesn't actually end? So let's grab a random number, and we're going to grab it from a uniform distribution, and we could run it from the beginning of the wave file to the end of the wave file, but I'm not going to do that. I'm going to run it from the first hermit thrush song time, whatever that is. You can see up here start times. The first one is 167.493. That's right here. And so there's, I don't know, almost 3 minutes of silence at the beginning of this recording. Not necessarily silence, rather, but a time when there isn't hermit thrush song. And so just knowing my lab and knowing kind of the research we do, sometimes that might be like the researcher setting up the recorder, stomping around in the woods, adjusting levels, putting something in the right position or whatever. And I probably don't want to be feeding that material into my machine learning model, or maybe I do. It depends what you're trying to create. But I'm going with the idea that that's the kind of thing I can already just weed out by just not analyzing those sections of recordings. And I want my machine learning model to be more sensitive than that. So I don't want to send it, I want to give it data that's like typical, not data that is a researcher stomping around in the woods. So I'm going to run this from the first song that's selected all the way to the last song. So that's start times -1. And there's always the danger that that could be right at the end of the wave file, that last selection, such that we might grab an image from the end of the spectrogram where it doesn't exist. Like, you know, if you try and grab a 1.5 second image from the last 0.5 seconds of a spectrogram, you're going to get an error unless you have some way of managing that, you know, with the length of the subsection. So what I'm going to do is I'm just going to subtract 2 seconds off of that. So I'm going to take it's the last selection minus 2 seconds. So I know I've always got at least 1.5 seconds for sure, because I don't really care about how close I get to the end. This is just kind of a ballpark. So that's going to give me a random number, and I can print that, and I'll get 5 random numbers, and these are ranging from 436, which makes sense, all the way up to, in this case, 2033, which, you know, our last number, we can see what it would be. Let's see here. It's 2247. So yeah, we're getting a random distribution from here. And what we're going to want to do is grab images as we grab these random numbers, but we got to be a little bit careful because we don't want to accidentally grab ones that are positives, because we could randomly just fall upon an actual hermit thrush song and slot that into our negatives folder, and now we're confusing our model. So what I'm going to do is I'm going to check whether this rand matches any of the start times. I remember start times is our actual songs. So the way I'm going to do that is I'm going to go for time in start times. I'm going to iterate through, and I'm going to check if the difference between rand, and we'll say the absolute value difference, because we don't care what direction it's in, which one's greater. We just don't want it to be within 0.2 seconds. So if that is less than 0.2 seconds, I want it to break. So it's gonna break out of this for loop. And then what I can do is use an else statement. So this is a for else loop, which I think is maybe something particular to Python, but they're kind of handy in these situations where you want to just check a match or something like that, go through a whole loop. Because if it doesn't break, if it never matches one of these within 0.2 seconds, it's going to hit this else statement, and only then. If it hits the break statement, it won't hit the else statement. So you can look those up and kind of wrap your head around them. It's a little bit heady, but once you get them, they are kind of handy. So now I'm going to run this image slicer or saver. Which we did last time. I won't go through that because it's exactly the same. But I'm going to make a couple changes in that I'm going to put it in my negative songs folder, because that's what it is now. And my start column isn't going to be from time, it's going to be from rand. So this is my random number that I just grabbed up here. So I've gone through, I've checked if it's close to any of them. If it's not, it's going to run this, and it's only going to iterate through the while loop if it did indeed save an image. If it hits this break, it's not going to iterate. And that way I can actually control how many images I get. Because on all the times where it picks a bad random number that doesn't work because it's an actual hermit thrush song, it's just going to go hit the while loop again without iterating. And so it's going to keep trying again and again and again until it gets them. So hopefully your like spider senses are tingling, and you can see there is actually a potential here for an infinite loop in a situation where you had too much overlap in your selections and you didn't have space for those random numbers to not be within 0.2 seconds. I know that's not the case on these recordings, but you should always think about how it might crash or how it might break. And of course, you could fix that by having some other iterator that counts how many loops you've done and kicks out after, 10,000 loops or something. Or there's various ways you could try to solve that problem, and you could design this while loop in other ways. But this is going to work. It's going to give me 5 images in my negative songs folder. You can see I was playing around already, but I'll delete these. And if I run that, sure enough, I get some images. And you can see this might be the beginning of a hermit thrush song in the second half. And that's good because the first half doesn't have it. So that's exactly what we were looking for. This is just blank nonsense. So that's good. That's a negative. This is hard to tell. Like, it looks like it's probably not a hermit thrush song. I would have the assumption that it's not, but I'm guessing you probably can't look at these because of the stretch and if you're not familiar with spectrograms, you might not know. But yeah, this is kind of just noise. And same thing here. So this passes the smell test in that these are actually negative songs. Whereas when I go to my positive songs folder and look, I definitely get a clear, vivid hermit thrush song that's bright. And hopefully your own study species or your own sound that you're looking for, whether it's an instrument or an animal or whatever, that you can kind of double check and see that this is actually making sense. So all we would need to do, this one only grabbed 5. All we would need to do is instead make this while loop run till length of start times, which we know is 447, and it would store 447 images. And it would keep running until it gets 447 random start times that don't match the hermit thrush songs. And then we would have 2 folders, each with 447 images, and one folder's positives, one folder's negatives. And of course we could do that for every single wave file that we have selection tables for, and we could create thousands of images in that way. So hopefully some of the principles here at play help. And I know not everybody's data is going to be organized in this way, but if you kind of look at the principles involved and some of the loops and some of the code, you might be able to kind of adapt it to your situation and think about how you can scrape thousands of images together, hopefully without having to create them individually or curate them individually, but instead kind of use some principles and some problem solving to get a database that you can then feed into a model. And in the next video, we'll actually look at how to put together the model.